All right, so we're going to be talking about recursion, and I think, so I did do a brief kind of optional introduction last month that a few of you came to. So this doesn't, expect anything, but has anyone had any experience with recursion?
I did the pre-code platoon training.
Okay.
And we went over it in that.
Okay, so what can you tell me about recursion then?
I think I understand the flow well, as far as the idea is you have a base case, and what that means is in your function, you're checking to see whether the recursion should stop. And at the end of your function, you should return a callback to the same function. So it's calling itself again. And usually you're decrementing some value in the arguments so that your callback is changing.
Okay.
Where I tend to get lost is really knowing when it's most applicable. Like if I'm reading a challenge, seeing what about it is saying this should be solved recursively, or I know it doesn't have to. You can always write an iterable function to do the same thing.
Right.
But I never really recognize what the pattern is that says, hey, recursion would be really easy right here.
Okay. Yeah. So that's a good, that's a good introduction, and that's also a good, a good problem to have. It's very common. So today we're going to be focusing more on the kind of basic mechanics. So we're not going to be talking too much about, what's a good problem for recursion. We'll talk more about that on Monday. So you'll have to hold on just a little bit, but I'll throw out some stuff. Okay, so that's good. So there's a couple elements there. So the first thing is that a recursive function calls itself. So that's really the fundamental core of a recursive function. So we can write something like that here. So we can define a function. And then we can just call that. So what happens if I now call recursive?
It'll be in a loop because there's no base case to say when to stop.
Yeah, so this will go, will it actually go forever?
Well,
it'll go until the stack overflows, right?
Yeah. So we'll talk about this in a second, but so when I execute this, Python has some built-in limitations. This is configurable, but we'll see what happens. So I get actually a recursion error, and it says that maximum recursion depth exceeded. So the Python interpreter by default will only let you go about like 1,000 levels deep. So someone mentioned Stack Overflow.
Yeah, that's just what I've heard it called before.
Yeah. So can you tell me about a stack? What is a stack?
So basically, on a recursive function, everything that's executed gets put into into a queue. It doesn't actually happen when it's called. It gets kind of put in a line to be called, and so you're stacking things together every time that recursive function goes through something that's going to give you a return value. They're all stacked, but it's not until it gets to the last one that it starts pulling the things out of the stack and executing them. So I guess in this case, Python only allows you to stack up 1,000, function calls.
Yeah. Okay, good. So I'm gonna illustrate that really quick. So I'm gonna set a breakpoint here where I'm calling this function, and I'm gonna run the debugger over here. Run and debug. So what I'm doing here is this Python file will get executed and it's going to stop right here. And notice down here we have the call stack. So we have some variables up here and we have some optional things you can, if you want to pay attention to a specific value, you can put that in there. But here we're going to focus on the call stack. So here's the call stack, and the first thing that's on there is module. So you can think of this as like the main thread or the default execution context. So when you run a file, the way it works is, Brian was saying, is that every time you call a function, that will create a new stack. So we'll run this and we'll see. So now I stepped into this function, and so it was stopped here initially. Now this line 10 gets executed, and notice that I now have something on the call stack. So what this is doing is saying, I'm going to execute your program, but I kind of have to almost defer or create kind of another execution context to handle this function call. So I'm going to execute your program, and then I'm going to say, oh, I have a function call. I need to stop. I'm going to create a new stack, which you can think of as basically like an object. And this new stack is going to contain information about this new execution context, which is going to be this function. And we don't have anything interesting happening here, but this stack will have information about local variables and all kinds of other stuff. Then if we keep going, this function will execute. And once this function returns, then that stack, that execution context gets removed, popped off, and execution continues. So that's the basic idea. So you call a function, you create an execution context that it gets put onto this call stack. Now we can have two. I'm going to call function 2, which is going to call function 1. So would anyone like to take a guess as to what's going to happen here?
I think first, the function 2 will put something on the stack. And then inside of that, the function 1 will run its object. And then as they run, the function 1 will essentially come out first.
Right. So function 2 is going to call function 1, and function 1 is going to return something. So I can return this as well. So if I were going to print out, function 2, what would I get?
1.
Yeah. So I'd get 1. And how many call stacks are going to get created?
I think just 2.
Yes, yeah, 2. So the thing is, though, there's kind of a hitch here where it's not just going to be 1 and then the other. It's actually going to be 1, and then on top of that will be the second one. So this function is going to get executed. It's going to call this, and in order for this function to return, it has to call this other function. So it's almost like I want to return, so I'm function 2, so I want to return this value, but I don't know what it is yet. So I have to hand off to another execution context, another, item on the stack, and I have to wait for this to execute. So I'm basically like, I don't know what this is, so I'm gonna hand it off to you, and then this one will create a new item in the stack. It's gonna execute, and once that returns, then this function will know what the value is, and then this one can return. So we'll step through this. Okay, so we're here. We execute line 13. Function 2 gets called. So when a function gets called, it creates a new element in the stack. And now this function calls this function, which is going to create another element in the stack. And notice the order here, right? So func1 is on top of func2. So this is the first thing that gets executed. This is the second thing that gets executed, and the third one. And when things actually like resolve, then we'll see that the last one in is the first one out. So it goes first, second, third. But when the execution unwinds or resolves, it goes in the reverse order. So 3, 2, 1. So we'll see what happens. So this function is being called here on line 11, and this is going to resolve. And once it resolves, it gets popped off the stack. And now func2 has a return value here. So this is resolved. So now that can get popped off the stack. So now line 13 has this value, which we can see up here. Func2, the return value is 1. Does that make sense to everyone? Does that not make sense to anyone? Okay, so now that we have that basic model in mind, what's going to happen when we call? Let me create a breakpoint. So what's going to happen when we call this recursive function? I can even return it. Doesn't really matter, but
It's going to keep calling recursive and adding a new call to the stack.
Yeah.
Until it reaches that 1,000 break.
Yeah. And if there were no break, if Python, let you just do this forever, what would happen? Would it just run forever and ever and ever?
Probably have some kind of memory error.
Yeah.
It might crash your system.
Exactly. Yeah. So you would run out of memory. And why would you run out of memory instead of like my computer just burns up because it's running too fast?
Each function takes up a certain amount of memory.
Yeah.
And there's nothing ever to delete it because it's still waiting to be executed on the call stack.
Yeah. So you're creating, the issue is you will run, which maybe seems unintuitive, but you actually run out of memory because you're creating these objects. You're creating these execution contexts, which have information. They're basically objects. They have information about local variables and so on. So you're creating all these objects just one after the other, and eventually you're going to run out of memory. So we can call this, we can see here. So I can keep calling it. So this call stack is just going to keep growing and growing and growing and growing and growing. Right? So that's how it works, but obviously we don't want things to just call themselves forever. That's not a useful program. So what we want to do is have some kind of base case. So in a base case just means at some point I want you to stop. so we can let's write something that's approximately useful. All right. So we're going to write a function. So I should also say that recursion and loops are basically interchangeable. So there's nothing that a loop can do that recursion can't do. So, sorry, just give me 1 second here. Okay, sorry. So actually, there are some languages that don't have for loops, for example. They don't have looping constructs, and there's a reason why you might not want to have a loop, and those languages are typically functional languages. So the problem with a loop, so if we do for, let's just do, so we have a list of integers here. If I do for num in nums, I can do something like this. The issue is that I'm reassigning a value to this. So I'm mutating things, which is in functional programming kind of a no-no. So you don't want to do that. You don't want to mutate things. So that's one reason why some functional languages don't have loops. So instead of loops, you just have recursion, and that works fine. So you don't have to do this, but the kind of simplest form of recursion is just iterating or looping. So the first recursive function we're going to write is something that will count down. So you can pass it a number and it will count down to 0 or whatever we want. So let's write that function. So def countdown, it will take in some, take in a number, and we'll just hold off on this for now. All right. Let's do. All right, so anytime we write a recursive function, we need to ask and answer 2 questions. One is, when do we want to stop, and when do we want to keep going? So simply, that could be something like a condition. So under what conditions do we want to stop? In this case, so we want to count down from 10 to 0, let's say.
Yeah. Stop at 0.
Okay. Okay, so if something, so maybe we'll just do this pseudocode, base case, stop at 0. And what's the recursive case?
I guess before you call it, you'd want to like count down one. So like subtract from num, and then call countdown again. Right?
Okay. So yeah, so the point of the recursive case is to break down your problem in such a way that it gets closer to the base case, right? So if our problem is we have a number and our base case is 0, we need to somehow get this number closer to 0. So that will get us closer to solving the problem. So you can do something like print the number, and then we can subtract it, or you can just call countdown with num minus 1. So I'm just going to try running it like this as it is. Okay, and so what happened here?
Base case didn't stop it.
Right. So this ran, and it's, I got almost 1,000. And then once it hit 1,000 or approximately 1,000, the interpreter says, okay, I'm going to throw this error, probably like you've done something wrong here. So maximum recursion depth exceeded. So I didn't have a base case. So now let's write a base case so that this doesn't go on forever.
If num equals 0, return 0
Okay.
or return. Yeah.
Yeah. So in this case, since we're just printing stuff out, we can just do a return. So we'll run this now. And we see we're counting down. So if we want to actually include 0, we could modify this, but I'm not going to worry about those details. But here's the basic idea. So we could easily do this in a for loop, right? Just for, anyway, I won't write the for loop, but we know how to do this in a for loop, right? So the same thing works, and it works just as well. So this is kind of maybe uninteresting recursion to a certain extent, but this does, this does exist in the real programming world as an alternative to the loop. Okay, so we have countdown, we have a base case and recursive case. All right, let's do count up. So we want to start from, let's just say 0, and then count up to whatever number we pass in. Count up to 10 here.
You want to put an argument in count up for that number you're passing in.
Okay. Let's call it, we'll call it max. So we're writing a recursive function. So what are the first 2 things we need to figure out?
When to stop, when to start and when to stop.
Okay, so let's go ahead and write that out. So base case. So what is, we'll talk more about, divide and conquer and things like that later, but what is one way of thinking about recursive problems is what is the simplest thing you have to do? What is the simplest case where you will solve your problem?
Chad, do you mean like what kind of considerations should we be having for, like in this case, what is going to be the base case and what we're using to call itself to reach the base case? Do you mean that?
Yeah, so the base case in some way is the simplest possible problem. So recursion exists to solve a big problem by breaking it down into lots and lots of smaller problems that can be solved in the same way. So the simplest case, if we want to start from 0 and count up to max,
if max is what, less than 0?
yeah, or we could just say 0. Yeah, so yeah, we could do that either way. Yeah. So so if max, okay, so it's getting a little bit trickier here. Let's for now we'll do max. If max is less than 0, we'll do print max, and then what?
Else.
Okay.
Max plus count up.
Okay.
Winging it. Max minus 1.
Okay. So this is the right idea. Let me put this actually under here. Does anyone see any issues here?
Well, count up is starting at 0. So if you pass in 0, the first base condition is going to say 0 is less than 0. So print 0, and then that's it. It won't reach the else condition.
Okay, so that's it. But if we start at 0 and we want to count from 0 to 0, then that's kind of what we want to happen in this case, right?
You're counting up, huh?
Yeah, we're counting up. There's a couple minor
Max plus 1.
Okay, we could do that.
Oh.
So what's the problem now? First, I'm going to go ahead and add some.
Basically, it's just no, we don't need the max plus in the beginning, just the function itself plus 1. Like else count down max plus 1.
So what's the problem with this?
Yeah, adding 2 numbers, so that'll be 2.
You're starting at what you want where you want it to end, and you're going from there. You're not starting at 0. You're not actually. If the max is where you want it to end, you're not going to use a max plus 1.
Right. So I don't want this to change, right? I'm passing in 10. Here, I'm constantly increasing that by 1. So that's gonna, I'm never gonna reach my base case.
So you just want max.
But then I'm also not, my recursive case is now not breaking the problem down into something that can be resolved in the base case, right? Because I'm adding stuff to it, or if I just do this, I'm not changing it at all. So it's just going to keep running and running and running and running. So how can I think about this in such a way that I am trying to get closer to the base case? Does anyone have any ideas? This is definitely trickier than the first one. So is one variable going to be enough here?
So we can initialize num to 0 and do if num is less than max, and then
Okay.
do count up num plus 1.
That's what was throwing me off. We was missing a variable.
Right.
If I'd have had the num, then yeah. So then you could do max is
So
max
So-
is.
so
num
now
is-
we know that we're
Yeah.
probably going to need two variables. One, we don't want this to change, right? This is always going to be the max. But we want this to change. So what is our base case now?
When, yeah, when the base case would be when max
When it's
equals
less than
num,
max.
Okay,
equals
great.
equals.
Yeah. So if the max is the same as the num, we're going to print, we're not going to print the max anymore, but we'll print the num. So I'm going to call this with the simplest case 0. And that works. Okay, so the simplest possible case is that max equals num. So that's what we want to work towards. Now, if I do 1, then I'm not going to get what I want here. So we're going to have to include the recursive case. And what is our recursive case going to be?
Increment num.
Okay,
So num plus 1. Yep. Plus equals 1. Actually, it'll have to be inside the call. Count up max comma num plus 1.
okay. So it doesn't matter if we do it here or do it here.
I guess not, because it's gonna, as long as you call it, it'll keep incrementing.
Yeah, it doesn't matter. Because num is a value that's available here, and so you can increase it here and then pass it in, or pass it in here and it will evaluate. Either way, this will evaluate before it gets called. So let's try running this now. And let's try 10. So what's happening now?
We don't have a print statement for the number each time to count up from.
Okay. So print so it looks like this is working now. So let me see who we got here. Josh, can you walk me through this code that we have now?
So obviously your base case is your max is equal to your num. Num starting at 0. So once your base case is met, once num equals your max, then you're going to break out of that the recursion.
Okay, so walk me through this example. Every step that will happen. So count up, call it with 1.
So one is going to be your max, correct?
Yes, yeah, exactly. So yeah, so here we have this default, which means that if I pass in a value, then num will be whatever I pass in, and if I don't pass in anything, then num will just be 0. So I can call this with either 1 or 2 parameters. So here I'm calling it with just 1 parameter, So now when the first time I call it, what is max going to be and what is num going to be?
So max is gonna be 1, num's gonna be 0.
Okay,
So your base case is not met, so it's gonna go to your recursion case.
okay,
It's gonna print the num, which is starting at 0.
okay,
It's gonna increment that number, then it's gonna return the recursion case, and now your base case is met, so it's gonna break out of the recursion.
okay. So it's going to call this function again with num plus 1. So 0 plus 1 will be 1. So it's going to call kind of max 1, num 1. This will get met and this will return. Okay,
Correct.
so good. Yeah. So we're going to take a short break and then we'll get into a couple more complex examples. You guys can see my screen?
Yes.
Okay, cool. All right, so we're gonna do something that's slightly more complicated now, a couple more complicated examples. So let's say we have an array and we want to sum up all of the numbers in that array. So we have an array. And we want, so let's solve this iteratively first. There are lots of ways to solve it, so we're going to solve it in a few different ways. So any way you can think of to solve it, feel free to shout out.
What we doing? Counting down? What did you
So-
want us to do with it?
So I want to write a function that returns the sum of every integer in a list.
You can do a for loop and create a running total variable.
Okay. So total and then for num in nums. Total,
Plus equals.
okay, num. I'm gonna wrap this in a function. So like this, and we're gonna call some for loop. Someone is not muted. So I'm gonna call this Python example, and this gets 10, right? So that's what we expect. All right, so we have this function and we're gonna iterate over. Can anyone think of another way of doing this? Not using recursion yet.
Do it with a while loop.
Okay, yeah. So we can do it with a while loop. So that would be very similar. So I won't do that, but yes, we could do that with a while loop.
Some nums.
Some nums.
Yeah, the sum method.
Oh, sum, right? Okay, yeah. So there's a built-in method called sum, right? So we could do something like sum. So what does? Whoops. So that gives us the correct output. So tell me about sum. This built in.
Is it similar to like how the for each method works in JavaScript?
Okay. Yeah. So it will loop over. It's similar to for. So yes and no. Yes and no. So it will iterate. So for each. So what does for each do? What does a for each loop do in JavaScript?
I think it will iterate over the array.
Right?
And I don't remember if it creates a new array. And
Yes.
like, so, oh, it does, okay.
No, but that's a good thing to think about. It actually does not return anything. So a for each loop it iterates over every element, but it does not return anything. Map on, so there are some higher order functions in JavaScript, and Python has the same ones. So what are some higher order functions?
I'm cheating, but you mentioned map.
Sure, yeah, map. So map is the main one. So what does map do?
That one does return an array. It'll iterate through the array, but will return a new array.
Yes. So it starts with an array. It takes an array and a function basically. So it'll start with an array and it will execute a function, whatever function you want, on every element of the array and return a new array of the same length as the original array. So that's kind of that's the thing. So if I pass in this array, it will return me another array that has 4 elements as well. So that's map. So that's not going to work for this use case because we want to start with a list and end up with one thing. So is there a higher order method that will take in a list and return a single element?
I know in JavaScript, the reduce method.
Yes.
does it.
Yeah, exactly. So JavaScript has reduce. Python also has reduce. You have to import it, but it's there. It's in the standard library. So don't need to worry about this in particular. So there's something in the standard library called itertools. It's like a functional programming toolkit. And reduce is something there. So reduce takes in 2 things. It takes in a function and it takes in an iterable, in this case, a list. So it takes in a function and it takes in an iterable. So we'll get the first thing, so nums. And the first parameter is going to be a function. And the function, the way the function signature is, it will have 2 parameters. And the first parameter will be an accumulator, basically. And the second parameter will be whatever the current value is. So let me just write out an example. So in this case, we want to add everything. So accumulator and current and return. So let's just execute this to make sure that it works, and then I'll talk about it. Oh, it's functools, I think. Sorry. Okay. So this gives us the same result. So let's talk about how this works. So reduce takes 2 things. It takes a function and an iterable. This function requires 2 parameters. And the way this works is, for every pass, let me move this down here. So every pass through, it will take, by default, it will start with the first one. So this adder function will take the first parameter and the second one, so 1 and 2, and it will, in this case, add those up. So 1 plus 2, this is going to return 3. And then the return value for this one will get passed in as the first parameter here. And then the following parameter will be the current. So this will be 3, the sum of 1 and 2. And this one will also be 3, being this one. So then those two will get added, 3 and 3, which will be 6. So then 6 will get passed in as the accumulator, and 4 will get passed in as the current. So 6 plus 4 is 10. And then we're out of elements to go through, so this will return 10.
Isn't that the same thing of what some nums technically does, is it takes the first 2, adds them, and then grabs the next one and adds them to that, and then grabs the next one and adds it to that?
Yeah. Yeah.
It's essentially throwing in parentheses. Like if you think about it in math terms, if you were to write it out, it would throw parentheses around your 1 and 2 and say, add these. Okay, I have a 3. Now take your parentheses and throw it around 3 and the next digit being
Yeah.
a 3. So now that's 6. And then
Yes,
Okay.
yeah, exactly. So in this case, the built-in sum is just a special case of reduce. So we could easily implement our own subtractor. By just doing this. And that gets us -8. So, okay. We haven't really talked about lambda functions, but here reduce takes 2 functions. I've written out this other, I've defined this other function out here. Is there a way for me to do this inline here?
Arrow function.
Basically, yes. So in JavaScript, you could use an anonymous arrow function here if you wanted to write, a short inline function. Python doesn't have, arrow functions, but they have the same thing. So they have what are called lambda functions. So a lambda function is an anonymous function that you can inline basically. So if we want to do, I'm going to go back here and we'll just keep it as an adder. So instead of defining this function outside and then passing it in, I'm just going to define it inline. Has anyone used lambda functions in Python before?
Yeah, once.
Okay. Do you recall anything about them?
Effectively just that they're, like you said, they're anonymous unnamed functions. I used it for the calculate mode challenge the other day
Okay.
for rearrange. I used it for rearranging an array. Well,
Okay.
a
Yeah.
dictionary, but
Yeah. So for sorting.
yeah.
Yeah. So that's a common use case. So we'll write one here. So this is just the first exposure. Will seem strange probably. So the syntax is lambda. So you actually just have the keyword lambda and then whatever parameters you want. In this case, we're going to have an accumulator and a current. So lambda, we can call these whatever we want, and then a colon, and then whatever you want to return, which in this case. So this is our inline anonymous function, which is doing the same thing as this adder function. So we can run this, should also get 10. So we'll see more lambda stuff later, but so you just need the keyword lambda, and then you have your parameters, if any, and then a colon, and then this will be whatever gets returned. Okay. Okay, so I think that's probably good. So there are, lots and lots of ways of adding up a list. So let's do this recursively now. We're actually going to do it 2 different ways recursively. So some 1. All right, so some recursive one, it's gonna, I know that it's gonna take in a list of numbers, so I can pass that in. Let's see. All right, so how should I go about solving this recursively?
So I guess you could start with an if statement to check the length.
Okay, so yeah,
Well-
so we need to figure out two things. Anytime we write a recursive function, there are two things we need to figure out.
You need-
One is-
The base case. You
Okay.
need to define what your base case is. That's going to stop your recursive for your recursion.
Okay. And then the other one,
One to start it.
okay. Okay. So if we think about adding adding every element of an array, what is the simplest possible case we could have?
Run out of numbers.
Sorry, what was that?
When you get to the end of the number list, run out of numbers.
Yeah, so that would be the base case. I guess what I'm asking is what is basically the simplest possible input we can have?
Would be like an array of 1. Just
Yeah. So what would we return in that case?
One.
Right. So we would return whatever this is. So if we have an array 1, 2, 3, 4, the simplest base case is I take whatever the first one is, let's just say plus something. So I'm adding, so I need to add something to it.
You need to add something to the one.
In that case, it'd be return 0. right?
Okay, so yeah, we have a few options. It kind of depends on what we think of as the exact base case. But if I have 1, so I could do 1 plus 0. What if I have an array with 2 elements?
you would add the next index of that array. Like, would we need like an index to kind of pass in as an argument so that we can access that for,
Okay, yeah, so that's a good question. So we're thinking about, what information do we need to have for every function call?
You need the index. You need to add like num0 plus nums1, something like that for every call.
Okay. So we'll need to potentially, one thing we could do is take whatever element and then add it. So if let's take this case of 1 and 4. So if my base case could be potentially anything. So let's look at the recursive case. So I want to break down this complex problem into a simpler problem. So the simplest problem that I can think of probably is the simplest case is if I have an empty array potentially. So if I have an empty array, then I will return 0 or something. If I have a single element in the array, I will take that single element and add it to nothing or to 0. If I have 2 elements, then I want to break this down into that simplest problem again. So if I have 1 and 4, I want to take the 1 and break this into its own problem. So the 1 plus 0, for example, and then I will add that, whatever that is. So this could be like the accumulator. So I'll take that and then add that to, again, the simplest case, which is an array with a single element, in this case 4. So if I did something like, if I start with 1, 4, and I say, okay, I'm gonna break this into an element, let's say 1, and then 4, or this 4 could be anything. So we'll add this 7 just so it's clear here. This is the rest. So I start with this array. The first thing I'm going to do is break it down into a single element here. And then I can add this to 0. So 0 plus 1, I'll pull that out. And then that will be added to 4, 7. So we have 1 plus 4, 7. And then what we need to do here is repeat this. So we've gone through this step. So now what we want to do is we take this array and we're going to break it down. So this will now be 4, 4, and then the rest, in this case, just 7. And we're going to add it. We're going to add this first element to the accumulator that we have, which is now going to be 1. So 1 plus 4, and then we'll have the rest. And then we're going to have 5. And then the rest. And then we're going to do the same thing here. So we're going to take this element, which is the 7. And the rest will be do an empty array. So it's nothing. And we're going to take that element and add it to the accumulator. So 7, 5 plus 7, which is going to be 12. And then we have this empty array, which is our base case, and we stop. So the problem breaks down. It's a bit weird, but that's kind of the basic breakdown. Is we have this simple case where we're adding, we're taking in a single element and we're adding it to an accumulator, and then we're leaving off temporarily all the rest of the elements, and then once we have that value, we're gonna pass in the rest of the elements and to get chopped down. So our base case, the simplest case is we're basically adding an element, a single element, to the accumulator, and the recursive case is we're breaking down our original nums into smaller and smaller chunks. So there's a lot happening there, and it's very confusing if this is the first time that you're exposed to it. It's a different way of thinking about solving a problem like this. So I wouldn't worry if you're confused, basically. All right, so we have our base case here. So let's work on implementing that.
Hey, Chad.
Yeah.
So before you kind of go through it, just so I'm getting a better picture, when we're saying in this case we have our base case, do we want our base case to say something like if the length of the array equals 0,
Right,
Um,
yeah.
Okay.
Yeah, there are a few potential, so, you know, you won't necessarily always just have one base case, but here I think there's, you know, arguably just one real base case. So let's write that out. So if there's a couple ways you can do this in Python. You could do if not, an empty list is falsy. So we could do that in Python. We could also be a little bit more explicit and say if when nums 0, return 0. So just to be explicit, we'll do it this way. And then the recursive case. So the recursive case, how are we going to handle that?
We'll need
Turn.
an accumulator variable first, I think.
Okay, so yeah, so there are kind of two ways to solve this recursively, and we'll look at both ways. For now, I want to basically I'm going to say that we're not going to have an additional variable here.
If we're going off of kind of the example you were starting to write down when you broke it down into those individual steps, are we gonna want to pop off? Obviously, it's a JavaScript term, but are we gonna want to like remove the first element and have that act as the accumulator?
Okay. Yeah. So the recursive case. So we know at the very least that our recursive case, we're going to want to be working towards a list that's ends up being a length of 0. So we know that we're going to have to chop off at least one thing, right? So we can do that. So return some recursive 1. And we're gonna have to shorten this list somehow. So we can decide it doesn't really matter, since addition should be, you know, it shouldn't make any difference here. But yeah, so let's return nums. So what am I doing here?
You're calling
Slicing the
some
nums list.
recursive and passing in nums, starting at the index of 1 and going to the rest of the list.
Yeah. So this is going to be shorter. This is going to be 1 shorter. So I'm basically saying everything that's in nums. So if it starts out with, let's do this. So if it starts out with 1, 2, 3, 4. This is nums. It's a length of 4. This is not going to hit. It's going to return this, and it's going to return some recursive calls with 2, 3, 4. So the question is, what do we want to do with this 1? So we know that this is part of our simplest possible problem. We have a single element, right?
Don't you want to add num 0 to that some recursive call? Like on
Yeah.
the front end?
Yeah, so it's a little bit tricky, but what we want to do here is we'll do nums 0. So this is the one that we're kind of want to chop off here effectively. And we're going to add it to whatever this call returns. So let's look at a simple case, and we'll kind of step through it. First off, I'm going to run it, make sure it runs. And I'll print this. Okay. So We're calling it with this array of 1, 2. Base case does not hit. So we're going to return num0, which is going to be 1 plus this call. So 1 plus some recursive, and we're calling it within a list of this 2. So the first time, so I'm just going to make a comment here. So this will end up equaling 1 plus some recursive of 2. And do we know what the value of this is? Yeah, unfortunately we don't. So we're basically saying, okay, so I want to add 1 to whatever you are, but I don't know what you are yet. So that means we're gonna have to enter a new element on the call stack. So we're basically gonna have to hold off on this. So the next run through, we have some recursive of 2. Is the length 0? No. So that means we're going to chop off the 0th element, which is going to be 2, and that will be plus some recursive, and that will be some recursive of an empty array or an empty list. Okay, and do we know what this evaluates to? Well, we can check that out. So we're going to call some recursive with an empty array, and oh, that hits our base case. So we're going to return 0. So now this equals 0. So some recursive with an empty array equals 0. So now this has a real value, right? We have a real value we can work with now. So now we can start unwinding the stack. We've hit our base case. Now we can start building back our solution. So we have 0 plus 2, right? And that means that some recursive of 2 is 0 plus 2, which is 2. So now I have 2 plus 1, which is 3. So I have this final value now that I can actually return from the original call. So again, the stack is first in, first out. So, or sorry, first in, last out. So this was the original call we made, but it's the last call that gets resolved. So we call here, but we can't resolve this because we don't know what this is. So we basically have to pass it off to the next call stack, which is here. Once this resolves, this call stack can return a value, which means it can pass that value to this one, which means that this one can actually resolve. So let's take a look. We'll use the debugger and take a look at that. Okay, so we're calling, we have this print function, which we'll ignore basically. We have this sum recursive, right? So we're calling a function, which means a new element on the stack is going to get created. So we'll run through, the base case is not going to hit. We're gonna end up looking like this with another function call. And we can see, we can actually look at the information in each stack. So here's the first call where nums is 1, 2. And here's the second call where we've reduced our problem into a single element. So here's that, local variables. So we're going to keep going. Sorry, one sec. Okay, so we'll keep going again. and we add a third element to the stack. And notice that in this most recent execution context, nums is an empty array, which is our base case. So now we're gonna walk through again, and this time it will actually return. So this stack can now return 0. And once this returns 0, this stack can actually be resolved. So it's going to be 0 plus 2. And the same for the first one. And then at the end, we get 3. So it's a little bit bizarre because what's happening isn't entirely, it's not entirely transparent in our code itself. We're kind of relying on the call stack to hold information for us. So it's definitely a different way of thinking about this stuff. And
So can I
yeah.
ask a question?
Sure.
So essentially, it's not solving it in what you would think a linear fashion, right? It's basically storing your best way to put this. It's storing each set of equations until it hits the base case, and then it's going to, from the base case, start adding each one of those that it stored.
Right, because it will build up a solution. Basically, it's going to break the problem down into smaller and smaller pieces until you get an actual result. And once you get a result, then you can kind of unwind the stack. You can go back, you can reverse back to the beginning. So you're kind of breaking down the problem into all these little chunks in these different stacks. And then once you can actually return the value, you're going to set off a chain. So the issue is that, this first recursive call, it doesn't have a value. So it's basically just passing it off. You're saying, hey, sorry, I know you want a value from me, but I don't know what it is yet. I have to ask the next function call. And that process can continue, basically infinitely. But so you're going to keep passing the buck and saying, sorry, I can't return a value. I have to wait for this other function to call with a reduced problem space. And once the problem space is reduced to the base case, then that last stack actually has a real value. And once that stack has a real value, it can start passing that, it can pass that value to the next one down. And that stack can get resolved, which will allow it to pass a value down to the next one. So you basically have these like delayed function calls.
Okay.
But it's definitely confusing and strange. So again, if you're baffled, that's perfectly normal.
I have a question.
Yeah.
Are these recursive functions, are they going to be more efficient than like say a while loop or a for loop as far as like processing time or whatnot?
For something like this, no, there are languages that either prefer or require recursion instead of looping, and there are like Scala, for example, does something called tail recursion. You don't need to worry about this, but there's an optimization that can happen where it will reuse the same call stack for every recursive call. So it basically transforms recursion into like a loop. So in Python doesn't do that, doesn't have tail recursive optimization. So it'll just create call stack after call stack after call stack. And there are certain requirements you have to meet in Scala in order for that to work. But so I would say for something simple like looping or iterating, recursion is not going to be the optimal solution. But there are certain problems which we're not really talking about right now, but there are definitely certain problems that are fundamentally like recursive problems, like traversing a tree or a graph, which is more complicated. And we'll talk about that later. But and there are also, again, I don't want to get too in the weeds here, but there are things like memoization, where you can basically, if you execute a function and it returns a value, you can kind of remember that value. So the next time the function gets called with the same parameters, it doesn't have to actually execute all the code. It just, oh, I already know that value. So it's like a cache, basically. So that can solve some. There's some issues with recursion that helps solve.
I've got a question.
Yeah.
Is the call stack specific to the application? So basically you have 1,000 stacks you can work with any Python application.
Yeah, so that's something that's configurable. So that's a default configuration that Python does. You can change that. There's nothing like, I would say there's nothing strictly logical about choosing 1,000 as the limit. And again, other languages won't have that.
Okay.
But if in Python you're getting to the point where you're doing that, there's, you're probably doing something wrong. All right. So I think, yeah, that's probably good. It's been a pretty long lecture. Yeah, I think I'll stop here. So let me stop my